Okay, this is the sixth video for Chapter 7 and 8, the Intro to Quantum Mechanics. In this one, I think I'm finally going to take all that theory that we've been doing the last few videos and see where it finally leads to, shed some light on the chemical elements, and more particular how it actually led to the shape, kind of the unusual shape of the periodic table. Okay, so again, I want to focus on this little chunk of math. Had some scientists kind of pondering, because what they had already discovered is that there was definitely a pattern to the chemical properties of certain elements. And what they noticed is that about every 8 or so, at least for the light elements, you'd end up with a noble gas. And that wasn't true early on. Basically, helium was a noble gas, and then you don't see another one until like 8 protons and electrons later. And again, at this point, the number of protons and the number of electrons was fairly well known, at least for most of the known elements, the lighter elements. And there was definitely kind of this pattern, especially around the pattern of every 8 elements. For example, fluorine and chlorine have an awful lot in common chemically, as do lithium and sodium. And so there was this hunch that the number 2 and the number 8 were somehow significant. There was also kind of another property that the original theory hadn't even taken into account, and that is the fact that some elements have magnetic properties. Hydrogen, for example, hydrogen atoms, for example, are bent, are split essentially by a magnetic field into kind of two halves. And of course, obviously a lot of the metals have magnetic characteristics also. So anyway, what ended up happening here is that just by kind of noting, looking at these orbitals, it was easy to see how someone proposed that maybe for each orbital can have 2 electrons. This would explain why when n equals 1, you end up with a total of this now number of electrons would have 1 times 2, or 2 of them. And then in the second one, 1 plus 3 is 4, times 2 would be 8. There's our magic 8. Here's our 2-8 pattern. Now the next one, which is 9, has 18. We'll come to that in a second. But anyway, this actually, along with the whole the magnetic field thing, allowed a scientist named Pauli to propose that there was a fourth quantum number, which he actually just called spin, electron spin. So we have basically size, shape, orientation, and now another quantum number called spin. Okay, and Pauli also developed a theory that essentially was called the Pauli exclusion theory, that says no 2 electrons can actually have the exact same set of quantum numbers, meaning there can't be 2 that have n equals 1, l equals 0, m equals 0, and each have the same spin. Okay, so again, this extra quantum number was introduced for spin, and all of a sudden we have something that seems to make a little bit more sense here. Again, when we get to the third one, it kind of breaks down. What was interesting, and I didn't even draw the third row, but the third row again has potassium, and I want to say calcium. Yeah. And then if we skip way over to the one below aluminum, you've got gallium. But again, no one understood the shape of the periodic table yet, and so I guess they'd be inclined to basically say, well, there's 18 more elements before you get to the next noble gas. They knew the next noble gas is krypton, and they know that, and that had an atomic number of 36. Which again fits nicely. Here's 2, here's 10, here's 18, that's 8. Now we're adding 18 and we get to 36, so that makes sense. But now, all of a sudden, in terms of aligning like properties, it was a little harder to make this pan out, the shape. But then all of a sudden there was a realization that the actual the 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 elements, as we fill the periodic table up with every increasing element, essentially every new element that you encounter has one new electron. And so if you just basically say, okay, each electron, at least in the base energy state, is going to go into the lowest energy state available, then it allows us to what's called fill up the periodic table just by essentially saying, okay, we've got a new element, magnesium. It's got an extra electron. Where does that electron go? Well, it goes into the lowest energy state possible. And using that concept, they were able to completely fill out the periodic table. Now, as you can see, by looking at a real periodic table, it doesn't look like this. And that's because I intentionally drew this as though we hadn't made the jump yet to say that the periodic table is actually ordered according to the lowest energy orbital available for an electron. And this was the big jump that they made in finally coming up with the modern shape of the periodic table, is using the Pauli exclusion principle, essentially making use of the fourth quantum number, spin, and then remembering that every time you introduce a new electron, it has to go into the next highest energy state. It can't actually go into a state that's already occupied. So again, that's the exclusion principle. So every time you add an electron, because you're now encountering a new element that has one new electron, you have to put that electron into the next possible energy state that's as low as possible, the lowest one that's available, that's not occupied. Okay. So in doing that, this shape now all of a sudden becomes much more meaningful. And sure enough, when we get down into 4, I'll add that in also. There's 32 of these, and you'll see where that number comes from also in the periodic table. Okay, now, one thing I want to point out is that at first it's really tempting to say, okay, well, n equals 1, that matches the first row of the periodic table. Well, that makes sense because n equals 1 has 2 electrons. Here they are in hydrogen and helium. Okay, I get that. N equals 2, that has 4 orbitals, 1 plus 3 orbitals. 2 electrons each makes up 8, and that kind of makes sense from lithium all the way to neon. If you add it up, there's 8 in there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so far so good. Now n equals 3, 1 plus 3 plus 5, we should have 18. Why does the third row of the periodic table only have the same number as the second row, meaning only 10 elements? Okay, and I'll show you the reason why. Hopefully I can show it in a small amount like this. Is that, and first of all, now next I'm actually going to assign names to these groups. So when we talk about 1 plus 3 plus 5, for example, when n equals 3, the actual we actually name the sorry, let me say it differently. For the different L values, remember when I was talking about L, the L values can take on 0, 1, etc., but they only go as high as n minus 1. Okay. Now, each of these L values, and I'll draw it all the way to 3, for example. All these L values, which can refer to shape, also have a shorthand name associated with it. It's a letter associated with them. The L equals 0 is referred to as the S orbital. The L equals 1 refers to the P orbital. 2 refers to the D orbital. And last, 3 refers to the F orbital. It goes further, and the next one down would be the G orbital and then the H orbital. But those higher orbitals those higher shapes are less important in chemistry right now, and you'll see that in a little bit as well. But these 4 shapes are used, and in fact they're used as shorthands for the orbitals in question. Okay, so using that as a guide, I am now going to draw the orbitals using that shorthand, starting with the lowest energy orbital. So the lowest energy orbital, you know what? I think I'm going to erase hate to erase it because I might need it. And I'll leave it right now. The lowest energy orbital, way down here, is going to be 1s. Okay, so the 1s orbital is the lowest energy orbital. Again, that's where n equals 1. That's what the 1 comes from. N equals 1, and s is the shape L. Okay, so the 1s orbital can hold 2 electrons. Okay. Now, when we're talking about hydrogen, hydrogen only has 1 electron. So the hydrogen's electron is going to go into the lowest energy state, which happens to be 1s, and it's going to go in with a spin in this direction. By the way, a lot of times in the books they show an up arrow for a positive spin and a down arrow for a minus spin. I like to show it this way so that you'll see that when hydrogen or when helium comes around, the second electron for helium can also fit in the 1s orbital, which is the lowest energy state. So it will, in a ground state for helium, it will actually have a second electron in the 1s state, but it'll have the opposite spin as the first electron. Okay, so the 1s orbital, when filled, is basically kind of represents the first 2 elements in the periodic table. Another way of saying is that helium, the helium atom has 2 electrons, and the first electron is in the 1s orbital with a positive spin, and the second electron is in the 1s orbital with a negative spin. Okay. All right, then we're going to go up to the next highest orbital. Well, remember, for n equals 1, there's only one L value, which is 0. So there is not a 1p, because that's not a legal quantum state. But the next highest orbital is going to be also an s orbital, meaning essentially it's going to be quantum numbers n equals 2, L equals 0. Okay, that's the next highest energy state above 1s. So when we come across lithium, which has 3 electrons, lithium's going to fill the first 2 in the 1s, but then it's going to have 1 left over, the third one. It's going to go in the next highest energy, still the lowest one possible, which is going to go here into the 2s orbital. Beryllium, when it comes around, it has 4 electrons. It's going to go 1, 2, 3, and the fourth one is going to also go into the 2s orbital, but with the opposite spin. You can kind of see how this builds up. I'm going to break this video and I'm going to build it up, and I'm actually going to build it all the way to Krypton and show you the rest of how these orbitals play out.